Hi guys, just about to go through forces today for AQA Physics for Friday. Part of it will cover EdXL, which will be scale and vector diagrams. Hello. That part links over to EdXL, but I believe if you are OCR student, you did everything you need to do on forces. So today's lesson won't be useful to you. If you are studying OCR, you've done it all if you're studying OCR. So tomorrow I'll be doing waves, which is coming up in OCR and in AQA. So if you're OCR, there's no point in doing this one today. Alright guys, you should be able to see the screen in front of you. Tomorrow, Case, tomorrow I'm going to be doing waves and is it magnetism you guys have got coming up? I'm trying to think what else you got coming up tomorrow. Yeah, I'm going to be doing waves and electromagnetism and that tomorrow night. Tonight's just forces, which is you've already done in paper 1, so you won't need tonight's one. But tomorrow you'll need, I'm going to do waves and electromagnetic waves and electromagnetism and other stuff that's needed for OCR, but tonight is mainly for AQA. If you're studying EdXL, there's a tiny bit that can come up tonight, which is in the first couple of minutes. Okay, so awesome. So this is really mainly for AQA, but in the first couple of slides there's some stuff that will link to EdXL students and their paper 2 exam on Friday. Okay, got somebody in a bowling alley here. The girl is trying to knock down the 10 pins at the end of the bowling lane. Velocity is a vector quantity. Speed is a scalar quantity. Can anybody remember what a vector quantity is or what a scalar quantity is? If you can, put it on the chat. There's a slight 10 or 12-second delay between chat messages. That was just because in the last live I did, like, there were some people up just spamming, and that's just to sort of delay the spam. So you can still type lots of messages, but just there's like a 10-second delay. Yeah, Ruby, well done. So a vector has size and direction. Size and direction, or magnitude and direction. Scalar only magnitude. Magnitude's the fancy name for size. So and only has magnitude. Awesome, guys. Great answers. So now you may be given as just on the depending if you're doing the foundation or higher paper, it'll just be a few marks whatever paper you're doing on vector and scalar, either asking you to write something or tick a box. We're going to have a look at a couple of questions in a second. First of all, just to be able to spot, you can just memorize what one's a vector and what one's a scalar. My method of working out if something is a vector quantity is this. A vector quantity can have a number below 0. So if I say I weigh 80 kilograms, what unit is kilograms for? Does anyone know what quantity kilograms is a unit of? Anyone know what quantity kg is for? Nice one, Ruby. It's for mass. If I say I weigh 80 kilograms of mass, I mean that I am made up of 80 kilograms of atoms. Yes, this is for triple as well, but I do the triple at the end after I've covered the combined. So if I weigh 80 kilograms of atoms, can I say that my mass is minus 5 kilograms? Is it possible for me to be minus 5 kilograms? No, well done, Han. So, therefore, mass is a vector quantity. So, a scalar quantity can only have a value above 0. There's one catch to that. So again, like if I said how much energy is in this water, I can't have less than 0 energy. You can't have minus energy. So energy is scalar. So it's really simple. The only one that's a slight trick is temperature. Temperature, we can say, oh, in the winter it gets to -5, but that's because humans are a bit silly and we use the wrong temperature scale. A scientist uses a temperature scale called Kelvin, and temperature can't be below 0 Kelvin, absolute zero. So you can't actually truly have a negative temperature. So temperature is scalar. It's the only one that doesn't fit my little rule. Right, I'm gonna see if you guys can work out these questions. Okay, so let me just put up a question for you guys. Let's zing this out the way. Actually, let's just go. Bum, 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 bum. Okay, what am I doing? Here we go. Okay. Right, first one. Which of these are scalar and which are vector based on my rules there? God, that was hard work. I might have to move my face. There we go. That was a bit hard work. All right. Hi guys. So vector or scalar? Based on that rule that a scalar cannot have a number below 0, what do you think distance is? Speed scalar, velocity vector. Yeah, distance would be scalar. You can't say to somebody, I walked -2 meters to school today, or I walked -100 meters. Distance is a scalar quantity. Time's another one that's not on here. I can't tell you my live is starting in -5 minutes. Can't do that. So time is another one that can only go forwards. It can only be in positive direction. Let's have a little look. What about force? What about force? Is force vector or scalar? Backwards, you could walk backwards, but the distance is just how far you've travelled, so that will always be just a positive number. We don't tend to give it direction. If we start to give distance direction, it changes a bit. Force would be vector, that's right, because you can have plus 500 newtons or minus 500. You can push or pull something. Good. So the answers are like this. You can check whether you got them right. Distance is scalar. Force is vector. Speed is scalar. As soon as you give speed direction, it becomes velocity. We use the same equation for calculating velocity or speed. The only difference is with velocity, technically you should, if you're stating a velocity, you can give it minus. You could say I ran at -10 meters a second, which means you are running in a different direction. So yeah. As soon as you give speed direction, it becomes velocity. All right, there's one more of these, and then we shall move on. Hold on. I've got one more of these. Does this one overlap that one? It does. Awesome. Right. Yeah, I think maybe distance would become displacement if given direction. And displacement is the distance, the nearest distance between you and your starting point. So if I run a mile from my house and then I stop 1 meter, I finish back at my house, the distance I ran is 1 mile, but my displacement is 0. Or if I stop 10 meters from my house, my displacement is 10. So displacement is the distance you are from your starting point. But yeah, you start to get towards displacement. Okay, right. Which one's a scalar here, guys? Out of this list, which one's a scalar? And then we'll move off of this. Quite an easy concept, isn't it? Yeah, mass is scalar. People saying mass. Oh, that's because I've put my. Oh yeah, yeah. I see what you're saying. It's nice. Well done. Well spotted, someone. Yeah, I have to move my face around a little bit. Yeah. Thanks for that. Nice one, guys. Okay, it's my hay fever. It's messing with my head. Yep, cool. Two boxes. So yeah, distance and speed. Well done, Kadam. Ba ba da ba. Okay, let's move on, guys. What have I got going on here? I don't know. Okay, another quite easy concept, but something that can come up. Contact and non-contact forces. So let me just check you guys are cool with this. Don't know what that one's doing there. Okay, let me just check you guys are cool with this. Contact and non-contact. Quite an easy concept, but if I don't cover it and it comes up on Friday, I feel bad. So where's my camera now? Okay, let's just shrink my camera down a bit. No, that's moving the whole screen. We don't want to do that. Alright guys, got two tick boxes here. 3 ticks are needed. First one, gravity is a non-contact force, which means the objects that are interacting don't touch each other. The Earth and the Moon are both interacting. They have a interaction between them using gravity, but they're not in contact physically. So that's a non-contact force. What's the other one? Electrostatic. Nice. This is for AQA. Absolutement. It is forces for AQA. I guess paper 2, I mean, some people said paper 1 was so many maths equations. I mean, generally in paper 2 there's a 6 marker which involves 2 maths equations that you're going to get on the paper. We'll go over some of them later, some 6 markers with maths, but generally the one they've been doing recently is the spring constant and elastic potential energy. But who knows? We'll have a look at that in a bit. Contact and non-contact. Electrostatic. What about on the next one? Which of the following are non-contact forces? So electrostatic again. And magnetic. Absolutely. When you have magnets, the force of attraction, they don't have to contact each other to attract each other. Awesome. Right. So non-contact and contact is fairly easy peasy stuff. So let's go and look at what else I've got on here before I move on. There is a list in the description of what I'm going through today. If you're like, oh my gosh, I can't sit here for all of this, you might want to dip in and out. There's a list in the description. If you click, you'll see a list of the different topics I'm going to go through. And afterwards, I will timestamp it. So I'm learning all these things. So if you come back and rewatch, you can fast forward through and you don't have to watch all the dead bits which happen in a live. Alright, when the boat propeller pushes water backwards, the boat moves forwards. The force of the water causes an equal and opposite force to act on the boat. Yeah, so yeah, this is going through all forces. Yeah, so which law of Newton's is this an example of? You've got the first, you've got the second and the third. You've got to know your laws. So yeah, it's the third law, which is essentially uh, Newton's third law is everything has an equal and opposite reaction, or two interacting objects will exert an equal and opposite force on each other. I'm going through physics, not geography. Cool. Newton's first law is essentially that an object will maintain a constant motion and shape unless there is a resultant force acting on it. Cool, cool, cool. Right. What about the second one? Which sentence describes the relationship between weight and mass? Everyone agree with that? Let me zing this dude. Umar, afraid not, mate. You are on the way. Listen, if you're going to come on the chat and mash up people's revision, I'm going to have to get rid of you, unfortunately. Yep, yeah. I'm going to ban anyone that's being inappropriate. At the end of the day, the chat this is really about doing revision and stuff. So does everyone agree that weight is directly proportional to mass? I'm going through different questions from lots of different papers that cover everything in the topic. Yeah, weight is directly proportional to mass. Great. Yeah, they are directly proportional. Not the same thing. Weight is a force, the force of gravity acting on a mass, and your mass is how much stuff you're made up, how many atoms you're actually made up of. So nice. Right, looking at the orange, we've got a picture of an orange here, and what name is given to point X? Does anyone know what we give to point X, the name? Center of mass, nice. You all know this. So this is just checking that no one's going to get surprised tomorrow. They used to have a lot more on center of mass, but there isn't a lot to know about center of mass now. So that's coolio. Right, let me just open this one up. This is now, before some of you think, oh, that's so easy, sir. Some of these are higher questions, but you know, with higher questions, you still get easy parts. So let's have a look here what we got. Okay, so you've just located the center of mass all successfully, but I haven't gone through parallelogram of forces. I will be doing scale and vector diagrams and that type of thing shortly. I think if you look at the topic list, you'll see the ones. You'll find out quite shortly. If you look at my topic list for today, if you close out the chat, and by the way, if you close out the chat, hit the like for me. And then if you click on where it says AQA only forces, the title, click on the title, and it will come up with the topic list for today, and it will say I am going to go through these topics: contact, vector, scalar, contact, non-contact, weight and mass, which we're on now, free body diagrams and resultant forces, and then after free body diagrams is resolving forces and scale drawings. And one of those is parallelogram of forces, okay, which do come up in AQA. Rare, I haven't come up for a little bit actually, so scale drawings have, but the parallelogram particular one hasn't. So, and then you can just click back on the live chat and get yourself back in. Okay, nice. Right, all right guys, yeah, so today is mainly AQA, because if you're studying OCR or EdXL, you'll have already done all the forces. As I say, the only thing for EdXL people is they have those parallelograms and scale drawings, which is like third or fourth on my description. All right guys, center of mass, yes, but how would you describe it? What is meant by the center of mass? I'm not doing generators or magnets till tomorrow. Yep, that's a really good answer, Karen. Nice answer, SJ. Yep, good answer. Where the mass is concentrated. Awesome. Right, calculate the mean weight of the potato. Now, here's something where people are going to could make mistakes. What the potato? I can't even read properly. Calculate the mean weight of the tomato in Figure 1. Use the physics equation sheet. Now, you guys are actually being blessed with the equation sheet, so I'm going to give you the equation because there's no need for you to memorize it. So you got weight is equal to mass times gravitational field strength. So you'll need to rearrange that and tell me the weight. How are you going to do that? Well, if you look over here, you've got to read off of that. Now, I don't know if that's too small for you guys to read. 415 sounds good. We'll go with that because 415 newtons. Okay, calculate the mean weight of a tomato in Figure 1. Actually, that's grams. What am I doing? 415 grams. Okay. Okay, so if that's the mass, and I need to calculate the weight, I need to multiply that by 9.8. However, that would get you 2 marks, guys. What have we missed? And this is the reading the question bit. Read the question right from the start. What have we actually missed? You guys are all scoring 2 points out of 3. Units are there, the newtons are there. Newtons are there, they're giving us the units, they want the weight in newtons. Ah, hand spotted. We need the weight, the mean weight of a tomato. And they gave us right at the top here. So the point of this is not to colour it out like I've just done, but to highlight. I thought that was a highlighter. That's the rubbishest highlighter I've seen in my life. They gave us the mass of 5 tomatoes. So yeah, there's a few extra marks here. Yeah, so just watch out for that. You would have to divide. You can go 415 divided by 5. Would be helpful if I actually brought my calculator to the show. What did I do with my calculator? This is one of them lessons where you need a calculator, and normally I have my scientific calculator right. Oh yes, I've got one in my drawer. Superbulous. Alright guys, there's 5 tomatoes on the scale. So midget, 5 tomatoes on the scale, and the question asks for 1. Yeah, sneaky. You'll only drop 1 mark. If you mash that up, you'll only drop 1 mark. Let's assume it's 415. Divide it by 5. We get 83 grams. Now, mass should be in kilograms. So now we're going to divide by 1,000 and get 0.083 kg. And then rearrange our equation to do weight, to do mass times gravity, yeah, times 9.8, and we'll get newtons. And you can kind of spot there newtons per kilogram. We have to align the units, so if we tried to do that with grams, we would drop 1 more mark and only get 2 out of 4. There's actually a 4 marker. Hold on a minute. I've not rearranged that very well, have I? Weight is measured in newtons. Yeah, weight is a force, so it's measured in newtons. Now, I don't know. Yeah, that's 415 grams. 83 grams for 1 tomato seems really light to me. But there we go. 100 grams. So it turns out that there's 100 grams in 1 newton. 10 newtons is 1 kilogram. So this is less than a newton. Yeah, that makes sense. I'll make you kilograms, 800 newtons. Yeah. Okay, cool. Let's zing over here now to figure 1 contains a spring that oh, no. Let's not do spring constant. I want to get back. That's later on. I'm going to skip the rest of that question because I'm doing spring constant later on. Yeah, absolutely. That's exactly what they do. Verdant, this is physics P2 if you are an AQA student, as it says in the title. However, if you are studying Edexcel, this next bit is relevant to you. Free body diagrams and scalar drawings. If you're doing AQA, then everything on here is AQA. So, let's move my face because it's annoyingly there. Nice. Alright guys, this is a free body diagram. You might think, what the hell is that? That's when they draw a little picture of a car, or they pretend a car is just a circle and they say draw the forces acting on the car, and you do air resistance, you do thrust of the engine, or push of the engine, or you can do one weight which is going down. So I've got my boat here, and here where this black dot, this is saying this is the boat in this diagram. It's called a free body diagram. And they want you to draw the different interacting pairs on it, or the two interacting pairs. So complete the diagram for the boat. They just want us to add one more arrow. So where should my arrow be? Oh yeah, there's my charger. Okay, where should I add my arrow? Right, Karam is absolutely right. I need to add my arrow up, and it's got to be the same size. Why has my arrow going up got to be measured with a ruler to the same size and drawn with a ruler? Don't lose a mark because you haven't got a ruler. There may be something on the mark scheme that says if they ain't got a ruler, take the mark off. Don't lose a mark because you don't put the arrowhead either. So this is worth 2 marks, believe it or not. It's 1 mark for an arrow going up and 1 mark for it being the same size. So a nice 2 marks. Absolutely. Equal size forces. Now we could talk about this in terms of Newton's third law. We could talk about this in terms of Newton's first law. So you can explain this with Newton's first law. If the boat is not moving and it's stationary, then we know the forces on it are equal. And so we know that the weight is being balanced by the upthrust. If the boat's not sinking or not taking off, then we know that or we could do this in terms of the third law and say when two interacting forces exert a force on it, when two interacting objects exert a force on each other, the forces are equal and opposite. And that would be an explanation as well. Okay, calculate the mass of the boats. This is bringing you back to... Actually, we're not going to use that. We don't have to use this now. We have something else that brings mass into it. And this is Newton's second law. Where have I moved my... Hold on, where have I moved my little face to? I've moved it right there, haven't I? Yeah, of course I have. Alright guys, so one of the ways in physics, you've got, I might first of all think, oh, weight equals mass times the force of gravity, which we call G. So, and they've given me the gravitational field strength, but then I'm looking and going, well, I haven't got the mass, but I do have the weight. So you can actually use both of these equations to solve this. So who can solve it? You'll probably need a scientific calculator for today's lesson. You could use the one on your phone, but it might not be able to do everything. So what do you think here, guys? What's the mass of the boat? You could. How would I rearrange W equals mg to find the mass of the boat? Oh, someone's put, Karam has put mass equals weight divided by gravity. Absolutely. Absolutely, Han. Yeah. Newtons over 9.8. Super. What are my newtons, guys? What are the newtons? We've got the weight here. Oh, you don't know the newtons because you don't know the scale. I'm assuming that's clever of me. I'm assuming that's let's say that's 4 centimeters. So that would be like 20 kN. What do I need to do with the kN? I keep writing wherever I put my camera. What do I need to do with the kilonewtons? Times 1,000. Thanks. Yeah. So if I said that's 20 kN, I need to times 1,000. So we're going to end up with... I've probably just... Yeah, I've moved my face there, haven't I? All right. So we're probably going to do 20,000. newtons divided by 9.8. That will give me the mass. By the way, you can still use this because you've got the newtons there. So this would be, you can still use that. You might say, how can I use that, sir? We don't have acceleration. Can anybody tell me what the acceleration is acting on the boat? Midget, which forces are we talking about here? Oh, mass times velocity is to find momentum. No, the acceleration acting on the boat downwards. This is a dumb question, but the wait, I'll answer that one. The acceleration on the boat is actually is the same as saying 9.8. I know the boat's not actually moving, but gravity is accelerating the boat to the center of the earth at 9.8. I know it's a bit crazy, isn't it? But so technically you could use the force equals mass times acceleration, and you just replace acceleration for 9.8. Right. Someone has just said, I know this is a dumb question. It's not, by the way. What's the difference between weight and mass? Weight is a force in newtons created by gravity acting on your body. So if you go to the moon, where I believe the gravity is 1.6, something like that, then you will weigh, what's that, 6 times lighter on the moon or something crazy like that. So you'll be like 6 times lighter on the moon. So the best way to lose weight is to go to outer space, go to the moon, and you'll have lost 6 lots of your weight. You can divide it. However, you'll just be as fat as you are because all your atoms are in the same place, and that's your mass. So your mass is a measure of how much stuff, physical stuff you're made of. Your weight is the force of gravity acting upon that mass. Okay, and is measured in newtons, whereas mass is measured in kilograms. Yeah, weight is gravity times mass, SJ. You can say that as well. Yes, so if you go to Jupiter, you're going to put on a lot of weight. Jupiter's got a strong gravity. Yeah, I believe that's the right answer, but yeah, that should be the right answer. Right, you've got the principle. Let's move on to the disgusting stuff. Okay. EdXL people, you've got this coming up on Friday. As I say, OCR people, I've really got nothing for you today. If you're studying OCR, you've already done this, so honestly, don't waste any time watching the live, unless you're just, this is your way to relax, is to do disgusting physics. Yeah, Verdant, I'm going to cover all that tomorrow. An alternator is used to generate an AC current. Isn't it easier? I'm going to cover all that tomorrow, but you can ask away in the chat. Someone might jump on that. Right. Alright guys, what the hell is this about? Well, let's have a little look. Your AQA people, you've got to know how to do this, something that people drop quite a few marks. And even if you get some of it wrong, you could pick up a lot of easy marks on these type of ones. But if you don't have a clue what you're doing, you could lose all of them. So we've got a tow bar here. Some people, when they go camping or something, they have a car and they have a tow bar, and this is higher, yeah, higher. Some of it's foundation though that I'm covering, so I'm kind of covering everything for foundation and higher in one go. The resultant force of the tow bar on the trailer, but it's not triple. I haven't covered anything that's unique to triple people yet. The resultant force on the tow bar has a horizontal component and a vertical component. They've given us the numbers. Determine the magnitude, direction of the resultant force of the tow bar on the trailer drawing a vector diagram, sometimes known as a scale drawing. Now these can be real nice easy marks, worth about 4 marks, sometimes worth 5 marks if there's a unit or two to convert. So, all right, nice. Yeah, thanks for that, Midget. Right, so what do we do here? First of all, I need to create a scale, Okay, you see we've got this graph here and people hate scales. Try not to make a really small one. The examiner's not going to give you the marks. If you're drawing a graph, we're just doing a diagram, so you don't have to have it this big. But if you're drawing a graph in any of your science lessons, they have to come up, or exams, they have to cover over half the width or height of the paper. So you've got to cover at least half. Like, you can't be drawing a graph that's that big. You won't get the marks, okay, for scale of your graph. So now with this one, I just want to make sure, look, 200 newtons. So I reckon my scale is going to be 1 centimeter is equal to what's a good scale to do? What do you reckon? No, this isn't triple, this bit. What's a good scale to do on this graph? I don't know how many squares there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so yeah, 25 sounds awesome. Who said 25? They're a hero. 4. There we go. 8 centimeters is my 200 newtons. Well done. I've gone for 1 centimeter for 25, okay? Yeah, you could do 50. That would be cool as well. 25's nice because, look, I'm only going up 3 centimeters for my 75. So, look, this is worth 1 mark. What I've just done, you've just scored the first of 4 marks. So if you get this and you get a story, but they give you a horizontal and a vertical, if you've been given the horizontal and the vertical force, you've got to calculate the resultant. We've just scored a mark, okay? Beautiful. We'll take that. Now, what you need to do next is join these bad boys like that with a ruler. By the way, if you don't use a ruler, obviously you're going to mash it up, but I don't know how to do that on this. You need to stick an arrow on your resultant force. Sometimes, depends. I'm going to put an arrow there, whatever. Probably won't need one. I've got the mark scheme here so we can look at it in a second. Okay. So, I now need to measure this with my scale. Using visual alone, without a ruler, who can tell me how long they think this line is in centimeters? Really good. Prerak, I don't know if I've said your name wrong. Forgive me if I haven't. G12. How do you know how many centimeters to draw the horizontal line? Well, it told us there that it's 200 newtons. You choose the scale. These are scale drawings, they're known as. And these are coming up in Edexcel and AQA, combined and triple. So, you choose the scale. You could have drawn that to any scale you want, but you must retain the same scale. So, someone came up with the genius of 25 newtons per centimeter, which allows me to just do 325s for the 75. So you could use Pythagoras if you're into that, but visually, what do you reckon, guys? If you were just looking at this visually, you might know, what do you call the line that's opposite this line here? Well, we know that angle's 90. We're not interested in that angle, but this line here, this, where am I? Oh, laser pointer. This line is going to be bigger than 200. Right? If you measure it to scale, that is probably going to be like 8.3 centimeters or something. So I'm going to say it's 210 newtons because I don't have a ruler I can use straight on the screen. Okay. So, yeah, hypotenuse. So you just work out that there. You can use a bit of Pythagoras if you want. Right. That scores you another mark if you work out the force. We've now bust out 2 of the 4 marks. Okay, your next mark is for the angle, and there's 3 correct answers here. 3 correct answers. Lovely, 213, thank you. No, you can assume this is 90 degrees. Vertical and horizontal, they're going to be at 90 degrees, absolutely. However, that's not the direction of this angle. There's 3 ways you can measure this angle. You can measure this angle here with your protractor. So bring a protractor for the exam. You'll need it for this. You can bring a protractor and you can measure the angle here. Now, just using eyesight alone, I'm going to say this angle is 70, right? And if you want to use this angle in your answer, you're going to say 70 to the vertical. So the direction is 70 to the vertical. If you're like, nah, that don't make sense to me, I'm not using that, you don't have to. You can do this. And you can use the angle to the horizontal over here. So the angle here that we've got going on there, I have no idea what that is, but again, that's 90. So I'm going to say that's 20. And that would be like 20 to the horizontal. I need a protractor to know. But so you could give the direction as 20, but then you've got to say to the horizontal. And the third way that they give directions is something called a bearing. So if they ask you for the bearing is this angle. And if I know that that's 70, my bearing is 290. You don't have to write all these angles. Please don't write all these angles. Just pick one. So bearing of 290. So that's my direction. I'm just going to go with like 20 degrees. Okay, that's a good question. What does the angle represent? The angle represents the direction of the resultant force. You know, we drew that force on that line you call the hypotenuse or whatever that line is. That's an angle, but yeah, whatever that line is, you mathematicians. It's the angle of the resulting force. Determine the magnitude and direction of the resulting force. So if someone is pulling you this way with 200 newtons and another person is pulling you that way with 50 newtons or 75 newtons, what's the angle of the direction you're heading in? You're going to be heading somewhere in between the two people, and the angle that you're heading in is 20 degrees to the horizontal, or 70 degrees to the vertical, or a bearing of 290. Yeah, so that is the north. So 290 from the north or whatever. Let's have a look. Let's have a look. So answers are over here. So what do we score our marks for actually? Because there's 4 marks here. So yes, just for the drawings, 1 mark. Resultant force in the correct direction. Oops, I put mine in the wrong direction, so I lose that mark. So you've got to draw an arrow on that line going in the correct direction. Resultant force with a value in the range of 218 to 212 to 218. Okay, I lost that mark as well because I put 210. But I'd use a ruler, or you can use your trigonometry for this. So someone put down 213. Who put down 213? They got it right using their trig, 213.6. Anywhere between 212 and 218 they'll take. Allow a calculated value of 213.6 or 214. So they're saying if you use trig, you've got to get 213.6 or round it up to 214. But if you use a ruler and measure the length of the line, you could go to anywhere between 212 and 218. And the last one is for the 78 degrees or 70 degrees to the vertical, 290, a bearing of 290. Yeah, or 20 to 21 degrees from the horizontal. But if you just say an angle with the little angle there, you can just say 20 degrees. Okay, enough of that one. Oh no, jeez. All right, last one on this disgusting stuff. You can't use the angle from where your original force is you have drawn intersect. Thank you, Callum. No. So you can't use your original angle because it's not going to be heading in that direction. Okay, here we've got horizontal of 150 newtons, vertical. So it's exactly the same answer, exactly the same method, 4 marks. However, we go in that direction, okay. And then there's obviously the dinghy. This dinghy is getting pulled upwards as well. Okay. But it's going in that, yeah, okay. It's getting, yeah, right, let's do that. Okay, so I guess the direction of the force is going to be in between these two forces going that way. But let's have a look. Horizontal, 150, that's nice and easy. Let's just do 1 centimeter equals 10, and I just need to do 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think that's 15. Gosh, I don't want to spend too long on these horrible things. If they don't come up, waste a lot of time on them. 150 newtons horizontal. Use a ruler. You lose a mark if you don't use the ruler. And then 50 newtons going upwards, just 5 centimeters, guys. That is the most disgusting line as well. So this angle is 90. We don't need that angle. That's not relevant for us. The forces are going like out there. I've done my forces wrong, so let's rub that force out. That's going to screw me up. That force needs to be on the other side. I've just looked at the direction. Can't be over there, can it? So it's on the dinghy. Yeah, it comes up fairly often. It's come up in the last 3 years. Does that mean it's going to come up again? I don't know. People always ask for predictions. Predictions are quite easy to make. The papers that I've done predictions on, I've got right. But like I did a prediction for the A-level biology paper 2, and I got that right. But it takes me about 2 hours to do a prediction, because what you got to do, if you guys have got spare 2 hours before Friday, fine, but I haven't got a spare 2 hours before Friday to do the predictions. But if you go through the 2018 paper, 19, 20, 21, 22, and you pull out your revision guide, so if you've got 2 hours to do this, actually you could probably do it in 45 minutes. You open up the AQA website. If you're AQA, if you're EdXL, open up the EdXL. You go to the chapter, pages on the chapter there, and you look through these pages and you look at the 2018 paper for paper 2 physics, and every time you see a question and you identify the topic and go, ooh, that's motors in electromagnetism, you write down 2018 by where it says motors, which will be on this page, in electromagnetism. And then you do that for every single question until they're all on there, 2018 written on these little dotted lines. Then you go to the 2019 paper, you look through the paper 2, you work your way through, and every time a question comes up with the topic, so if it's contact forces, you go to forces and you write down next to contact forces, you write down 2019, and then you get a picture of the last 5 years what they've asked questions on. And then you can make a little YouTube video and make millions of pounds by saying, guess what, guys, they haven't asked this in 5 years, this is coming up, revise this, but make sure you revise everything else, but just revise this. Yeah, so yeah, it has worked. Oh, parallelogram. Hey, potato. Yeah, I'm just waffling. That side for the vertical. I don't know why I've done that. Why have I done that side for the vertical? I guess because my drawing over here, it told me that it's acting on this dinghy over here. So my force is on the dinghy. It tells me here that it's on the dinghy. So the forces are going that way, and then it tells me there's a vertical force. So it's like that. So cool. Nice one, guys. Right, I will do there is a parallelogram question which is slightly different to this, which yeah, I should probably load up. The parallelogram is slightly different question, a slightly different style of answering it. So we'll have a look. I've got one which I could load up for the parallelogram question. What I was going to say, guys, what do I do next? What do I need to do next here? Anyone spotted what I've got to do next before I get off of this topic? What do I need to do next? I'm only going through forces today, so I've got to join these lines. Okay, predictions. What is... yeah, predictions. Yeah. So... how long is that line? How long do we think the... it's always longer than the horizontal line when you get one of these scale drawings. So I think that's going to be... I take rough guesses. I'm going to go that's 161 newtons. I need to get my ruler out and measure it, but yeah. I don't think this is A4 on my screen, so this is irrelevant. But tomorrow, on Friday, this ruler could save your day because you can just measure that and then apply your scale. times the centimeters by 10 on this scale. This is higher, but yeah, I'm going over some things. So you work out the resultant force. I'm not sure what it is. I'm going one. Yeah, I like that. 158 to 160. We've got the answers in the bottom right. I'm about to open them up so you'll see. Direction, this always screws me up. I'm going to be hands up. These scale drawings, they mess with my head. So 3 marks, right. We've scored 1 for our beautiful scale of 150 and 50 newtons. We've scored, I know that answer's going to be in the range. I'll bet my house on it. We've scored the 2nd mark for the answer in the range. We need the angle. It's going to be similar, isn't it? I don't know. I've got no idea what this angle is going to be. I'm going to guess at 30. I'm probably going to be totally wrong. And then you could do this angle to the horizontal, so to the vertical. So this is the angle to the vertical. This is known as the angle to the horizontal because it's the angle on the horizontal. You don't use this angle, which is always 90 that you've drawn. Or you can do this angle as the bearing. No, you can't use. Let me circle the one you can't use. I should have really circled that in red. You can't use that angle, and you have to state what angle you're using. So you have to say the vertical angle or the horizontal angle as the direction. So you have to say the dinghy is moving at 20 degrees, 30 degrees to the horizontal. The dinghy is moving at 70 degrees. That looks like, if that's 90 there, that's going to be 70 again, isn't it? You can just tell visually. So that's going to be, the dinghy is moving at 70 degrees to the vertical. And then we could say the bearing is 290 because you take the 70 away from 360 to get that circle around the outside. How do we know the vertical force upwards is on the left or right? From the picture, I'm guessing. From the picture. Because if the horizontal force, if this was reversing, it'd be like that, and then I would do it like that. But it says it's going horizontal force forwards. Look, the horizontal force is forwards. I'm guessing the vertical force is there. I don't think it's going to make any difference, maybe, potentially. And the 1 mark I can never get on this, I never get this mark right, is the direction. Let's have a look. I know you might say, how can you not get it right? But there we go. Physicists are insane. Okay, right. Yeah, those are the answers. Vertical force 50 newtons, 150 horizontal, resultant force, value of the tension 156 to 160. Damn, but I didn't measure it. So the value of the direction, the one to the horizontal, which it has in brackets, you don't normally have to say that. So allow 18 from the horizontal to 20, 70 from the vertical, and a range of 288 to 290 with the bearing. They call the bearing the one around the outside of the top. Okay, let's move. Let's go. Let's leave this. I'm not doing another one of these. This one's sick. All right, I'm going to just sketch this one fast, super fast. So with this one, they've given you, this one you've got to draw the angle yourself. They've given you the cable. They've given you the hypotenuse, or whatever you call that dirty long angle in maths. It's been 30 years since I took my GCSE maths, so forgive me, I forget the names of certain bits to do with maths. They've told us this is 20, so how can I draw that line? I can't really, because that's got to be 20. So I can start with a horizontal line, draw 20, get the protractor out and draw that to 20. Okay, I know the angle between the horizontal and the cable force is 20. Okay, so you might be saying, how do I know this? Cable, I think this was in the last 2 years this one came up. So tension in the cable is 2000. So we know this is 2000 newtons. It's the cable makes an angle of 20 to the horizontal. So I'm going to get a mark, I guess, for drawing the 20-degree angle, get my protractor out and draw that. And then it says draw the vector diagram, and this time they want you to calculate the magnitude of the vertical and the horizontal forces. So I would make 1 centimeter. Oh, move my screen. man. I would make 1 centimeter 400, something like 400 newtons or something here. That way I can measure this out. You get your ruler out and you measure that line. You do a 20-degree angle to the horizontal, and we know that that line there, which I've circled, which says cable, we know that's 2,000 newtons. So I'm going to measure a 5 centimeter line on my exam paper at a 20-degree angle. So this is my 5 centimeter line. And then I'm just going to draw my horizontal line with my ruler until it perfectly goes down at a right angle there. So I need to make sure that's 90 degrees there. Then I know I've got that perfect. Now measure this in centimeters here and times 400. So I don't know what that's going to be. I'm going to 1.5 centimeters. My angle should be, it's 20 degrees. That should be a lot shallower than what I've drawn there. So that would be like right down there. So, and then measure this angle. That's going to be, I don't know, that's going to be that's going to be like 1,800, I reckon. What would that be in centimeters? I was going to say that's 4.5 centimeters. So that's going to be 1,800 newtons. And 1.5 centimeters is going to be 600 newtons. So, is everyone cool with that? Yeah. So watch out for these scale drawings, guys. So you can see suitable scale, correct direction, triangle completed, showing correct components, scale used, 1,900, 680. Basically, you need your ruler to actually measure it and make sure the scale's correct. But essentially, once you pick your scale, you need to measure the lines and multiply the centimeters by what you chose 1 centimeter to be, and then you'll get the correct answers. Alright, let's get off of disgusting scale drawings. What is this? What the hell's this about? What topic's this, guys? I'll do Excel physics tomorrow. This is all AQA today. It's all forces, guys. Yeah, I would make sure the triangle's 90 degrees. Yeah, this is Hooke's law, Fletcher. Some people don't call it that. They call it the law of extension, or the law of proportionality, or the law of whatever. Yeah, that's right, midget. That's right. Yeah, the practical thing. Yeah. So, what is the law of proportionality, or Hooke's law? Does anybody know? So Robert Hooke was a scientist. He liked to get excited with springs and stuff. And essentially, if I just, let's delete, no, don't do that, Tom. Go back there. Okay. Can I rub that out? Ah, there's no point really in rubbing that out. Alright, let's not bother rubbing it out. Okay. What can we say about force and extension on that part of the graph, guys? What can we say about, oh, someone said extension is directly proportional not to mass, to force. You can convert mass, and those are masses, by the way, that are attached to the spring, but you convert those, you'll multiply them to find 100 grams is equal to 1 newton, 10 newtons equals a kilogram. So you'll multiply those to find the force. So what we can say, force or extension is directly proportional to force. What objects, this isn't the same for everyone or every object, what objects does this law apply to? This is the law of proportionality or Hooke's law. Both are correct. What objects does this apply to? Thank you, midget. It's for an elastic object. So make sure you know this is for an elastic object, not just any old object. Something like a spring, a rubber band. And you can prove if something's elastic. I take out my charger and I say, is this elastic? I can prove it. When I double the force on it by adding weights, does the extension double? because directly proportional means if you double one thing, the other quantity should double too. If it doesn't, then it's not an elastic object. Okay, but also, what's the other rule of elastic objects? More important than force and direction. What happens to an elastic object when you take away the force? Oh, I thought I had an elastic band. I haven't got one. What happens when you take away the force? So here's one of my daughter's elastic hair bands. If I apply a force, it stretches. What's going to happen when I remove the force from this band? Thank you, Midget. Thank you, Fletcher. It returns to the original shape. That's actually more important than the bit there that I've already put there. So you do need to know elastic objects return to original shape once force is removed. Now, it doesn't have to be an extension force. Does anyone know what the opposite? Another question. Does anyone know? I can't get all these down as notes that are worth copying at all, but does anyone know what the opposite? This is called extension. What's the opposite of extension that you can do with elastic objects? Does anybody know? Karam, thank you. Compression. So you can compress them, okay, which is squishing them in, and the same rule applies and the same laws should apply when you get on your mattress. If you've got one of these mattresses that is guaranteed for 20 years, then the springs should retain their elastic properties. When you get on your bed, go down. When you get off your bed, returns to its original shape. Okay, you're compressing it, not extending it, compressing it. But it should return to its original shape. And all of the equations and stuff still work with compression. You just change the E is just technically, instead of for extension, it stands for compression and it fits in. Right. What's happening here, guys, at what's happening here at P? Depending on the exam board you do, you will label that with a P, and it doesn't matter if you label it with a different symbol if it's the correct symbol. Does anyone know what that P is? Thank you. That's the limit of proportionality. Thank you. Limit of proportionality. You guys, you're giving the AQA answer. Now, depending if you were studying international GCSE, you label it with an E. And it's called the elastic limit, which means when you go past the elastic limit, it no longer returns to its original shape. It no longer behaves like an elastic object. In AQA, they call it the limit of proportionality. You can label it E or P, no matter your exam board. They're both scientifically correct. Okay. Yes. If you go past that point, it won't return to its original shape. So you need to know that. What do we call an object then that behaves like this when you apply a force? Now I've gone past that shape. Is that an elastic object? Basically, what is the word for a not an elastic object? Does anyone know? Inelastic, thank you. Good. And I like the word you use, deformation. Thank you. Deformation. Deformation means changing shape. So you can say an elastic object is one where when it's deformed will return to its original shape after. An inelastic object will not return to its original shape. So it's inelastic deformation. Deformation just means changing shape. Right. This equation you'll be given because you're in the last year that they're giving the equations out, which is good and bad because you don't get the easy marks for saying, remember the equation? Point for that. So, force is equal to K times E. Now, K is the spring constant. So, essentially, if you were going and buying a bed at the supermarket, do you buy beds at the supermarket? I don't think so. But if you buy mattresses at Dreams or one of these bed shops, you can choose different strength springs which have different spring constants. The higher the spring constant, the stiffer the spring. Okay, the stiffer the spring. Okay, the more force it's going to take to change shape. Some people prefer a stiffer mattress and other people are like soft mattress they sink into. So That's what you go spend your thousands of pounds on. You need to test them out. But a spring constant is a measure of how stiff an object is. So basically what I'm getting at is if you have a spring with a high K, a spring constant, it's going to be stiffer. Okay. Now, and probably be able to take more force before it becomes deformed. Okay. So let's look at the practical a little bit. I'm going to give you a question on the practical in a second. Practical here, it doesn't matter your exam board. Actually, it does, because Edexcel and OCR have already done this, but they have this practical too. So what you're doing here, can anybody see? This was a 3-mark question. This photograph here, okay, this one over here, where I'm sort of scribbling all over it. Can anyone see the 3 errors the student made? What they're trying to do is find out the extension of a spring. What are the 3 errors they made? Someone was asking about how long the live's going on for. Let me just check what the boom boom boom. What I want to do is hit my. I can tell you if I look at my. Geez, am I only there? Oh my gosh, how long have I been going? Raw, I need to speed up. I have a habit of waffling. Yeah, thank you. Rulers bent, spring non at 0. You guys are awesome. You're all over it. Yeah. So you need to find a way of keeping it straight. Don't forget, if you've got a 6 marker, wear goggles. I know you might say, why wearing goggles? If the spring snaps, licks you in the eye, you're going to be blind. You're going to go blind. So goggles on. You need to measure at eye level. Some of the other things to remember if you get this as your 6 marker: attach a piece of tape or card to the bottom. So attach a piece of tape or card to the bottom. It makes it easier to read because you're reading across a gap like that. If you have a piece of card attached to the spring where it touches exactly on here like that, it's easier to read. So you can just say stick a marker or a piece of paper card at the bottom of the weights. Make sure the ruler is dead straight. You could use a spirit level or put it on a flat surface. And make sure you measure the original length of the spring. A lot of people forget. If you say, how much has my hairband stretched? They get their ruler out and they go, oh, where's 0? Okay, 0's there. They go, oh, this has stretched 10 centimeters. Of course, it hasn't stretched 10 centimeters. It has not stretched 10 centimeters because I need to take the original length. So it's about 7. It's probably stretched about 2.5 centimeters. So don't forget, don't make the silly mistake of not minusing the original length from the final length to find the extension. A lot of people do that. Now, yeah. So, also another little sneaky thing the exam board can do on you. You don't need to measure the distance between the floor and... Oh, yeah. The height there. Absolutely, yeah. Yeah, that's a good point. That's a good mistake the person's made as well. I don't know what they're doing there. Yeah. Now, the other thing, watch out for this. Sometimes the graph doesn't start at 0. If it says, actually, the graph should start at 0. This would start at 0. But if it says instead of extension, if the exam board are really sneaky tomorrow, and they put something like length of spring, then the spring is already 5 centimeters, so it can't start from 0. So they might make an error and say, what's the error? That they should be measuring the extension and not the length. So just watch out for that. Because, of course, your extension starts from 0. But if you're measuring the length of the spring, it already has length before you start your experiment, so it's not at 0. Okay, that's about it really for that. I'm trying to think what else. Eye level, card at the bottom, straight ruler. Yeah, that's about it really. If you want to find they may ask you. There's a 6 marker on this. Come up quite a bit. This comes up quite a lot as a 6 marker. They may ask you how to 6 marks. How do you investigate or prove whether a spring is elastic? So then you can do the adding the masses, plotting it, until it no longer doubles. So when I double the force, it doesn't double, and then you'll say, right, I found, and you can plot the graph and find where P is, and then say, right, it's not elastic, and all of that rubbish and baloney. This is just displacement. So this is just an example of displacement. There's hardly any questions have really come up on displacement, so draw an arrow to show the displacement of the cyclist. Yeah, so thanks. Kilo is 1,000. That's 10 to the power of 3, Karam. Very good. Mega is 1,000,000. Giga is a bill. And Tera is what's a trillion. So, yeah. Think of on your computer, if you're downloading something, you've got kilobytes, megabytes, gigabytes, and then terabytes. So if you've got an Xbox with a terabyte hard drive, it's, yeah, whatever that is, 1,000,000,000,000 bytes or something. So yeah, kilo, mega, giga, tera goes up in 3 zeros each time. And then we go down in 3 zeros. So we go to milli, micro, nano. Can't remember what's after nano. It might be pico. Right. Yeah. Pico's pretty unlikely. It won't in physics. Pico doesn't come up in physics. It comes up in biology. We're measuring the mass of chromosomes and things. Right, guys. Where should my arrow be? Midget. Yeah. Distance, height, length. Extension is normally in meters. Sometimes they'll change the unit and say, look, we're happy for you to do this in newtons per centimetre or something. So. Yep, thank you, Fletcher Wallace. It's a straight line from home to the school. So that is the displacement. Again, if you had to measure that and they give you a scale, you can measure the displacement. The displacement is the distance from the finishing point to the starting point, the origin. So, like I said, if you run out your house now and you run 5 miles, your distance is 5 miles. If you get back to your front door and stand still, your displacement is 0 because you're right back at the starting point. So displacement is your final distance from the starting point. Yep. Yeah, so it's like the bird's eye. Yeah, like yes, it is. Yes. So displacement, the best way to say displacement is it's the distance between the finishing and the starting point, not the distance travelled. It's the distance, the shortest distance between the finishing and starting point. Yeah, it is a vector. It's got distance and direction. Oh, good gosh. Time for water. Right, acceleration. Super easy. So I just want to write that, but it's wrong. But I normally do that. It's just the accelerate. But of course, you need to do the change in velocity. How do we represent change in velocity, guys? I covered that at the start. Galland XEYT. Someone can update you on the different. Scalar is just size only. Vectors have direction. Yeah, delta, or some examples love to do this. This is your final velocity minus the initial, so that's totally fine as well. It'll probably appear like that in your equation sheet. V is your final velocity, and your initial. You're going to get it. They're going to say, oh, he was running at 20 and then he speeds up to 30. So I'll give you a little question, see if you can work this out, and then we can move on to the difficult acceleration, which is uniform acceleration. So let's say John runs at 20 meters a second, then sees his friend and accelerates to 32 meters a second in 3 seconds. What? What is his acceleration? So, what do you reckon, guys? Can you solve the riddle? It's not too hard. Yeah. That's super fast. John is very motivated to catch up with his friend. We'd all like to know why and what that's about, but I am going live tomorrow. Because a lot of people got an exam tomorrow morning, so I'm gonna go live tomorrow night. But I'm not gonna cover forces again. I don't think, because P2 isn't that bad. It's actually quite a good exam. But when you got to teach forces, forces is just long. Like the content in forces is just long. So I'm gonna have this done, and then it reduces what I've got to do tomorrow, because AQA do forces and it's long. Thank you for brilliant. What's the unit, guys? So we go final velocity is 32 minus the initial velocity is 12 divided by this guy is divided by 3. His acceleration is pretty cool. I think his initial speed was the most exciting thing. 4 meters a second. Yeah, we need the little 2, guys, because we are doing seconds divided by seconds equals s with a little 2. Lovely jubbly. Right, now let's get on to the difficult, nasty stuff. Okay, let me go through a nasty one here. So everyone cool with that? I'm going to do magnetism tomorrow. So if you're wondering about magnets, I'm not doing magnets today. It's just forces today. I'm going to do magnets tomorrow. Magnetism. Yeah. I'm going to do waves, electromagnetic waves as well. And then any other things. Right. Watch out for this. This one's, you have an equation on your equation sheet that looks like this. Again, depending on your exam board, their rearrangement of the equation is different. I believe AQA's is like that. It's called uniform acceleration. Okay. Alpha. No, not alpha, beta, gamma. That's nuclear radiation. I don't know if that's coming up for anyone tomorrow. I think everyone's done that in P1, but I may be wrong. So that's different. That's particle, although gamma's not particle, but gamma is cool. It's diverse. It crosses topics. It's in nuclear radiation and electromagnetic waves, because it's not made of a particle. Well, unless you believe in the wave particle theory. Now, velocity squared is equal to, blah, blah, blah. How can this come up? Okay, what was I on about? I'm waffling. Right, here we go. Let's go John again, the amazing runner. Right, John drops a coin off of the Eiffel Tower. It's my French accent. So he's going to drop a coin off the Eiffel Tower. It hits the floor. What do we reckon? 70 meters a second, right? I'm going to tell you something. Calculate, I can't even write. Calculate the height of the Eiffel Tower. Right, now some of you might be wondering, I believe, although I've written S there, I believe in AQA, I may be wrong here. I may be wrong. That's definitely an international GCSE, they use an S. But in AQA, they may use an X here. And it really gets on my nerves. I'm not a physicist. I'm not a true at heart physicist. I like physics, but I'm not a true at heart physicist. So, love it, Karam. Karam's all over it. This is where 90% of people, if you get this uniform, this is a 4 marker, guys, or 3 marker, a really hard 3 marker, or it's a 4 marker. Now, Karam's all over it. He spotted the thing straight away. You're going to panic. You're going to go to your equation sheet. You're going to say, I've been given speed or velocity. You're going to be looking at kinetic energy, half mass velocity squared. Oh my God, it's not that. I don't have the other thing. You're going to go to your acceleration equation and go, I've not got the time. I've got I've not got the time. How can I do velocity over time equals acceleration? I don't have the acceleration. So you're going to be panicking at this stage. You actually have lots of data here, as Karam said. If you drop something, so if I drop my mobile phone, before I drop it, the velocity is 0. So we now know that u is 0. Okay? So someone can calculate the height of the Eiffel Tower here. U is 0. Okay? Because U stands for initial velocity. We know the final velocity is 70 meters a second. We know, what else do we know? We know acceleration, and this is the bit that fools people. If you jump off a plane or you throw yourself off the Eiffel Tower or I drop my phone, gravity accelerates everything at 9.8. So if we don't take into account air resistance anyway. So if we don't take into account air resistance, gravity is going to accelerate at 9.8 meters a second squared. Well, that's the unit. You don't square it. But, God, I can't write. So we now know all the data that we need. And by the way, x, depending on what exam board you do, x is distance. I've always wondered why they don't use a d. But they don't use a d. I don't understand it. When they do moments, you use a D. When you do other things, you use a D. I don't know why in physics they do that sometimes. Some exam boards use an S there. I'm not sure. Okay, so can people... I don't recommend jumping off the Eiffel Tower. It's not a good thing to do. There's too many good things. Okay. Right, has anyone calculated it? 35 meters. So I need to rearrange this. Now, obviously on a live, it's very possible that I mess this up. So let's go. Let's go v squared minus u squared. First of all, take away u squared from each side. Is that right? Does it sound good? I bloody hope so. Then divide, as I just made all these numbers up. So then divide by 2a. Does that sound right, guys? Some of you guys are like level 8 or 9 at maths. Surely you can tell me if that's right. What answers do people get? "250 meters sounds right." I just made this up. We've got some varying answers. Let's go through it. Look, if you want to, you need to isolate x. X is the distance, so we need to isolate the distance on its own. So you're going to minus u squared from each side. Which is like minusing 0 from each side. But yeah, if you minus u squared from each side, then you're left with v squared equals 2ax. We can then divide each side by 2a, and we'll get v squared over 2a, essentially. So essentially, v squared was 70, so we go 70 times 70 equals 4,900 is 70 squared, and then we divide that by 2 times 9.8. No, that's definitely wrong. What have I done wrong there? Oh, thank you. Oh, thank you. Yes. My calculator didn't like that. And then you get that. Oh, my calculator is so rubbish. Yeah, so it's 250 meters. Woo! Yeah, basically 4,900 over 19.6. I hope you guys aren't as not really. No, it's my, sometimes I click the mode button on these calculators, and then you need like a degree in Casio FX85 to like get your calculator working. So once I start doing it individually, once my calculator goes like that and I can't reset it back to its default mode, I have like tons of these, then I just then I have to do everything individually. So it's just, you can simplify this because u is 0, so 0 squared is 0. V squared minus 0 is just v squared. And then so you're subtracting u from each side, guys. You need to subtract u from each side, and then because this is a times 2 times a, it's not in a plus or a minus, we can't add or subtract that from either side. We have to divide that to get that over to we have to divide both sides by 2a, and by dividing both sides by 2a, because if something's being multiplied and you want to move it to the other side, you've got to divide it. So we get over 2 times a, and then that equals x, and that should be 70 squared, because we know that v is 70, it told us in the question, over 2 times 9.8, which is 19.6. My calculator decided to be a beast and starts doing funny things when I try to combine everything together. It's just one of the modes I've got it on. No, they will. AQA will sometimes give you A. Sometimes you just have to know off by heart it's 9.8. They've done it before in the higher triple higher kids where they're just like, yeah, take that. And they've not even told you that it's about a falling object. When it's a falling object, you're like, then they're going to do it. Okay, guys, just to show you one more of these, this live's going to go on too long because I have just been waffling. I meant to spend like 1 minute on half of these. Right, let me show you another one which can get you. This is the same thing. Watch out for these tomorrow. Watch out for these. This is a 6 marker. Check, check, check. 6 marker. And this is what in P2 they love to do. They're going to combine 2 equations. If you get a 6 marker with numbers and it's a 6 mark calculation, 100 million %, you have to select 2 calculations from the equation sheet, right? And you'll know which ones to select by circling the data and going, right, I've got distance, I've got time, I've been given acceleration. So you could, if you want to write time, write acceleration, and then you could write D, you've got distance. Now, what can I calculate if I have acceleration and time? It says calculate the minimum braking distance of the car. What can I do here? Yeah, these 2 equation questions are definitely coming up, guys. Definitely coming up. It's Friday. So what we do here is I would look at the A and the T and immediately go, right, I haven't even read the question, but the camera recorded 2 images of a car 0.7 seconds apart, so we have the time. The car traveled 14 meters in between. We have a distance. The maximum deceleration of the car is 6.25 meters per second. They've given us A, the acceleration. I feel like we're going to be using uniform acceleration and the normal acceleration. Calculate the minimum braking distance for the car at the speed it passed the speed camera. So it's gone past the camera. We can work out the velocity it's going at, and then it's going to brake and stop. When it stops, what's its final velocity going to be? This is a really hard one. What's the final? Thank you, Galaxy. We can do velocity over time, but we don't know the velocity, so we need to use acceleration equals change in velocity over time, and then we can work out what the acceleration is. No, that's just the acceleration. There's no final. That's just the acceleration. So what you're going to do here, guys, you can do change in velocity v minus u over t a. The only equation you can use starting off with is that one, because you've got A, you've got T, you've got 2 of the elements. If you don't like to write it like that, you can do it like this. A equals delta change in velocity over time. Let's find out what the change in velocity is. So 6.25 times t. So we put these in a triangle. I need to multiply t by a. So I'm going to do 0.7 times the change in velocity, sorry, times the 0.7 is the time, and I'm going to times that by A, which is 6.25. Anyone with me here? Yeah, this is going to be like seriously hard. Yeah, so when it stopped, Karam, it's going to be 0. We're going to come on to that later. Someone's worked it out. Thank you, bro moment. So, 4.375 is not the change in acceleration. 4.375 is the change in velocity. So we know there was a change in velocity. We know the velocity the car is traveling at. We might even be able to just put this all in. I didn't even think about putting this all in. So, where's the... what's the blasted equation again? Yeah, this might be all mashing up everybody's head. It's mashing up my head, I can tell you that. I'm spending far too long on some of these topics. Right, absolutely. So that's your initial velocity, 4.375. So we now have all of the things we need to then use this equation, essentially. Okay. So essentially, it asks you about the braking distance. When a car brakes, it eventually stops. So we know final velocity is 0. So we know this is 0 equals. So 0 is equal to 4.375, which is, we've just worked out the speed of the car. The change in velocity, essentially, we've worked out the velocity of the car. So we know the car is going at 4.375 plus 2ax. We need to rearrange all of this. I'm assuming. I'm assuming if we just do the same. We want to find the distance, so we just do the same thing. Yeah. I don't think I'm... So we know the initial velocity. We need to get x, so we need to do v squared minus u squared. So v squared minus u squared, right, let's get on it. 0 minus 4... Oh, yeah, I'm going to go down here, right. So, initial velocity, final velocity 0, minus the initial velocity. What we're doing is rearranging this equation, v squared u squared plus 2ax, and we're just going to do it the same as we did before with the dropping a coin off of Paris. So that is then going to be divided by 2a, and that is going to equal x. So I need to square 4.375, however. So I need to square that. Okay. And that is squared as well, but we know what 0 squared is. So 0 squared minus 4.375 squared. So we're going to go 4.375 squared, 19.14. So I get 19.14. I'm going to call it 5. And that's minus, and that is over, what is the acceleration? 19. What was the acceleration? 6.25. 6.25 times 2 equals 12.5. That don't seem right to me by any stretch of the imagination. Nah, naught is final. I think this is a bit convoluted. Yeah, that's 100% the wrong answer, but we'll come back to that. I'll edit that one out the live. I don't normally make mistakes on the line, but that's 100. There's no way that car is traveling at, what was the speed that car was traveling at? 4.375. That don't even sound like it could be traveling at that slow speed. That's traveling at some seriously slow speed. If it's traveling at that slow speed, the rest of it is fine. But I think I might have calculated the velocity wrong at 4.375. I suppose not. It only travelled 14 metres in 0.7 seconds. Yeah. Okay. We'll go with that. Cool. Let's rock. We'll go with that. I'll check that one out later. I think it's right, but I'm gonna go for it again. Okay. Watch out for let's move on, as I'll never get through and get to bed, and then I'll be knackered for tomorrow's live. Right. Distance time, guys. DT graphs. Not a lot to say. These don't really come up in the high. If you're doing foundation, these are your friend. They're going to come up. Watch out for these. On a DT graph, you have distance next to time. So what you need to know is, can anybody tell me what is happening at A? If that's a distance time graph, what can we say is happening at A? Gradient of the distance time graph is the speed. Distance over time equals speed. So the gradient's the speed. And if it's a straight line like this, it's not accelerating. It's a constant speed. It's not accelerating. Straight line on a DT graph is constant speed. As I said, speed or velocity, you can use either word interchangeably here. And then, can anybody tell me what's happening at B on a distance time graph? Not constant acceleration. Constant speed. There's zero acceleration there, because look, there might be some acceleration there, but yeah. Right. Yeah, it stopped stationary. Right, this is less likely to come up on a higher paper, but now I've said that, it's going to come up, isn't it? Okay, so distance time graph, nice and easy. All you can really do from this is work out the speed. You can work out yeah, and at B speed is 0, it's stationary. So this is a very limited amount of things you can do with a distance time graph. The gradient is the speed. If it's curved and not a straight line, if there's a curve on this graph, then it's decelerating or accelerating. There's a change in speed. Okay, it's not constant, but my graph doesn't curve, so I'm going to allow that. Now, let's get rid of these lines. Thank you. Let's get on to the more common one for you guys and see if you can crack the Da Vinci Code. So this is much more common if you're on the higher paper. This is a velocity time graph, and this means totally different things. Okay, so what I'm going to do is, guys, what's happening at A? Yeah, fluctuating speed, blue sky, is called acceleration. So if your speed changes, that is acceleration, a change in speed over time. Thank you, Karam. That's a constant acceleration. Now the velocity is getting faster. 1 meters a second, 2 meters a second, 3 meters a second, 4 meters a second, 5 meters a second. Yeah, this is Usain Bolt running here. What's happening at B? Although he's jogging, because he goes at 10 meters a second, or a little over, bit over 10 meters a second. All of those 100-meter runners do. They do the 100 in 10 seconds. They must be doing 10 meters a second. But I think they get up to like 14 or 15 in the middle. So, what's happening at B, guys? Constant speed. Thank you. No acceleration there. So don't get confused between the DT graph and the VT graph. Velocity time. Watch out, they will put speed time sometimes. The gradient. What's the gradient on a VT graph? What's the gradient equal to? Well, the gradient is equal to velocity over time, and we just did that with the whole v minus u, or delta v over t. So the gradient is equal to acceleration. Okay? Groovy. So the gradient is equal to acceleration. The straight line's the constant speed. Yeah. This is constant acceleration here. Right, groovy. Last thing that the reason they love this graph on the higher paper is there's a lot more they can ask you about this graph. And one of the things we can do, and do people know, how would we calculate how Ross, right. Calculate the distance traveled oh, that's disgusting. That's 5. Alright, calculate the distance traveled in the first 10 seconds. Who can tell me? That'll be worth 4 marks on your exam. How do you calculate the distance traveled here, guys? Distance traveled in the first 10 seconds. Area, nice one, Han. Area under the graph, Joel. Spot on. Now, speed over time does give you the distance, but here you've got some issues because it's accelerating and the speed is constantly changing, so you can't just do speed over time. So let me show you what you've got to do here. Now, if you're totally baffed as to doing this with the graph, it's worth 4 marks, so you really want to be on this. You draw a line here, and you can change this into you can do the trapezium method. I draw wonky lines. Okay, I'm going to calculate the area of this rectangle, right, under the graph, and then I'm going to do this. Now, this is my method. There's other people with much better methods than this. My method is then to calculate this blue area and divide by 2, because I've only got half of that under the graph. So that's going to be my method. Let's race and see who can calculate the distance traveled. So I've got to work out what each little square is. Alright, look, just chuck that out there. You can just do the trapezium, Manny, but you have to have some math skills for that. So some people who don't have as good math skills might want to do this method. Right, each one of these little squares is worth 0.5. So on my method, I would go, right, I've got 6 squares at the bottom there, and I'm 5 up. So I've got 6 baby squares on my red bit that I've shaded red. They are worth 0.5 each. So they're worth 3. So I'm going to go 3 times 15 equals 3 times 5, sorry. About to make a mistake, equals 15 meters. So there's 15 meters in the red bit. Let's check out the blue bit. Right, the blue bit goes up to 10 minus 3. That's 7, because each of those little squares, if you're wondering, by the way, some people in the chat will be wondering how the hell do you work out how much one little square is worth. You take the fact that there's 10 squares there and it goes up to 5. So you go 5 divided by 10. You divide the number by the number of squares leading up to it. So I've gone up to 5 there. You can work out that each baby square is worth 0.5. So here I have 7, and I'm going to do 7 times 5, and that equals 35 meters. But I've calculated the area of a big blue fat rectangle, so I want to divide that by 2 and get 17.5 meters, add to my 15 meters, my total distance is 32.5. Hey, anyone else work this out? Yeah, I know. Yeah, so any of you guys good at trapezium method? See, I did my crap non-maths person method. I did my rubbish non-maths person method and got 32.5. So you might want to try the rubbish non-maths person method. You simply block it off into rectangles, and where you hit a triangle, you turn that into a rectangle. Now, they will give you marks on the mark scheme. If this is 4 marks, they will give you marks for working out sections. So they'll give you like 1 or 2 marks just for showing you attempted to work the area out. So if you're there and you're like, oh no, it's the area under the graph, but I can't work it out, draw on the graph and show them that you're attempting to work out the area underneath. You will score marks for an attempt to work out the area under the graph. Okay, let's zing. Oh no, my gosh. Honestly, it's killing me, forces. That's why I did this today. It's absolutely killing me, and it's far later. This was supposed to take an hour. I don't know what the hell. I just got waffling too much. Right. You guys need to know about terminal velocity and falling objects. So I'm going to start to try to speed up now and stop sort of... I'm going to try and speed through. Okay. So, got the dude falling. He's going to have 2 forces acting on him. We've got weight going down or gravity. Call it either one you like. And we're going to have drag going up. You might say drag. You call it air resistance. It's totally your choice. Air resistance or drag. Right. I'm using drag because it's smaller. I might even just use D and W. Easier to talk about. The graph shows the vertical velocity of the Skygyre during the first 40 seconds. His parachute is not open this time. What I want to know is... explain how he gets to terminal velocity. So what I'm going to do here is explain how he gets, I'm assuming he's a guy in this, he looks a bit mannish, but explain how he gets to terminal velocity using ideas, I don't know, about forces. Right, so we have to explain this in terms of forces. And what we're going to do here is, give me 1 sec, I'll just move that up there, zing back here, move that here. Okay, this is quite a common question for quite a lot of marks. And essentially, when you get a graph like this, guys, and it's an x-plane, and I've used the word explain. So when you get a graph and it's an x-plane, you need to break the graph into 3 sections, okay, that you're going to talk about. And you're going to get a couple of marks for each section. So first of all, initially, the man is accelerating as he's falling, okay? Why is he accelerating at his fastest here? I can tell he's at his fastest because the line, the gradient, is steepest. So why is he accelerating at his fastest? Anyone tell me, when you first jump out, why are you accelerating at your fastest? The line is steepest. So what we got going on here, weight at, thank you, G12, weight, all we do is say weight greater than D. I'm using D, by the way, and I'm going to use W just to shorten it up a bit. So weight, come on, weight is greater than D. This is what happens when you get tired. Right, weight is greater than D. So we have resultant force. What did Einstein say when you get a resultant force? Think of Einstein's first law. When you have a resultant force, you've got a change in speed. You've got acceleration. So that's why we have a change in the velocity over time. So I could also write acceleration. I've said force is greater than that. We have a resultant force. We have acceleration. Boom. That's scoring me points for here, guys. Make sure you talk about each aspect. Hardest aspect to talk about is here. This one is the most difficult, where I've just circled there. So what we want to say for that aspect of the graph, what's happening? People want to say he's slowing down. He's not slowing down. He's not getting any, he's going faster. Look, the line's still going higher. What's getting less? Yeah, not Einstein. Einstein may have come up with it too. You never know. Time machine. It's not terminal velocity yet. I'm talking here. The last bit's the nice easy bit where you can just bust out your terminal velocity. I'm talking here. What's happening here, guys? We don't want to miss this bit. Good. So we now want to say, that's a nice one, Karam, as he is at higher velocity, more collisions We love the old chemistry collisions. Per second with air. It's a bit long, I know, but I want to guarantee myself the marks if it's 6 marker. So increase in drag. It's still not bigger than air resistance. There's just an increase in the drag. So smaller acceleration or resultant force. So essentially, if I was drawing arrows to show you what's going on, here is W, here is D. At that bit there, he's just not accelerating as much. Your weight never changes. Don't start messing with the weight line, but the drag has got more. Okay, it's not quite there yet. W is still longer. It's not quite there yet. And then in the final section, in the final part here, we've reached TV, terminal velocity, okay? And all you need to say here is D equals W, forces are equal, so 0 resultant force, because, yeah, 0 resultant force, so yeah, we'll just do that. 0 acceleration I could put there as well, and I could say drag equals the force of weight. There's no resultant force. There's no acceleration. It's reached terminal velocity. Yeah, that's it, Joel. Super. Now, zing, 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 ziggity, zang. Oh, no. Yes. Person falling. They haven't opened their parachute yet. So what's my line going to look like? When this person opens their parachute, what is this going to look like? What's going to happen when this dude opens his parachute? Here's the misconception. This is the big misconception coming up that I would say most people get wrong, and they don't understand. There's a misconception here. Yeah, we're going to get a deceleration or negative. It's going to go like this. In fact, look at the first graph. We're just going to turn that upside down and slot that over. So it's going to go like this. And then a little bend there where it slows down. So it's a reverse of this graph. Look at the shape of this. It's a reverse of that. Straight, steep deceleration. Then the deceleration curves off as less air particles hit them. And then they reach a new terminal velocity until they lick into the ground. Now, here's the misconception, right? People get really mixed up with this. So, dude is coming down. Wait. He opens his parachute. Look at the drag. What is the bit that people find difficult about this? What do people find difficult about this? Absolutely, Karam. Higher air resistance because of surface area. But why do people find this concept difficult? What does this make us think is going to happen to the parachuter? It's unequal. Right, air resistance greater than weight. What would you normally think would happen to this man if someone said the force is bigger going up? You'd think he's going to go to outer space. He doesn't move a millimeter upwards, okay? He's still falling, even though the force pushing up is bigger. People find that very hard. They're like, hold on a minute, sir. The force going up's bigger, but he's still falling. Why is that? Because he has velocity. For him to go in the opposite direction, velocity is a vector quantity. I need to get his velocity to 0 and then change it to minus before he can go to up into outer space. So let's just say he was falling at 70 miles an hour. The drag is bigger, so he suddenly goes back to 50 miles an hour. He's still going down. He's falling at 50 now. Then he's falling at 30. He's still falling. For him to go to outer space, that drag would have to stay bigger. He gets to 0, and then it would have to go minus 10, minus 20 for him to go to outer space. So a lot of people get confused and think if the drag is bigger than the weight, you have to be going up. No. You're slowing down, but you'll never actually get it where it's bigger and go up in this situation, because what's going to happen is he decelerates. That is the incorrect spelling, and a physicist wouldn't use that word anyway. They'd say negative acceleration, but I'm not a physicist, so I'm going with decelerates. So he decelerates, D bigger than W. And this explains here, okay? We have a large resultant force. I might want to use the word large resultant force there. I should do. Now I want to explain, if this was a 6 marker, I'd explain this part of the graph, and I'd say, as his velocity decreases, okay, which is important, as his velocity decreases, what happens to the amount of air that hits him? Yeah, you can use negative acceleration. If he's slowing down, what's going to happen to the amount of air per second, the collisions per second? Air per second becomes less, right? Collisions. I'm writing this very shorthand. Air per second becomes less that's hitting him, and this means D decreases. So yeah, smaller resultant force. It's really long writing all this stuff out, isn't it? Smaller resultant force, less acceleration. So on the curve, there's less acceleration. And then we just get to this bit and we just say, that's our TV again, guys. Terminal velocity. And that's terminal velocity done, right? At TV, I need to say that D and W, drag and weight, or air resistance and weight, are equal. And there's no resultant force, no acceleration, constant speed, or terminal velocity. But I'm not going to write it because it takes too long. One more thing just before I move off of this topic, because I need to speed up. One more thing. Be prepared. This is one they asked recently. Look, this was asked in the last 2 years. Swimmer. Why does the swimmer have a top speed? It's the exact explanation we've just done for both of these, okay? But you're going to use water resistance. This is why drag's a better word, because you might start talking air resistance. Drag can be water resistance, it can be air resistance. Okay. So terminal velocity doesn't have to be falling objects. The swimmer at first is accelerating away from the boat. It tells us their speed is increasing. That's because the thrust or the force of their swimming, and in fact they help us out big time here by telling us the forward force. So the forward thrust is bigger than the water resistance or drag. Okay, so we have a resultant force, so their speed increases, they accelerate. Then we just say, as they swim faster, just like the falling object, more water per second hits their body, and this therefore increases the drag, and eventually the forward force and the drag are even, and there is no acceleration. There's no resultant force and no acceleration. They've reached terminal velocity. So that's why a swimmer has a top speed. Cool. Anyway, so that was the same as the falling object. And the shape of the graph would be exactly the same with 3 parts. So there's 3 sections. When you're talking about terminal velocity, just think of that graph leveling off. You need 3 sections. The bit where they're going really fast, then when their acceleration is only a small acceleration because the drag's increasing, and then the bit where both are equal. So, cool. Let's zing. Sod that. Right. Very quickly, do you know what? I'm going to end this live a little bit earlier than I didn't intend to actually go anywhere near this late. This is just me being an idiot and taking far too long. So, oh my good gosh. So I'll cover other forces. I might do momentum and then after this, and then we'll smash it on the head. Right. Right. What you got to do here, stopping distance, thinking distance, braking distance. The biggest mistake in this, what is that word there? The word here is distance. The biggest mistake people get is, if you're asked what the stopping distance is, you can just say the thinking distance plus the braking distance, or you can say the distance from when you see a hazard to when the car is stopped. Or you can say thinking distance plus braking distance. The biggest mistake I've seen in marking exam papers when I used to do that was students writing, they would say, what is the thinking distance? Guys, can you put up what the thinking distance is? Yeah, I'm going to go live tomorrow. I'm going through waves and magnetism tomorrow. I'm going through momentum after this, yeah. But can anybody give me the definition of thinking distance? I'm looking for someone to make the common mistake. Love it. You guys have all fallen for the common mistake. AG, ARU, you've all hit the common mistake. Bro moment, you've hit the common mistake. What did I ask you? What is the thinking distance? And what did you say? You started with the time. And I'd say 50% of students do this. Say, what's the thinking distance? And they say, oh, it's the time taken for the person to think about stopping the car. It's nothing to do with the time. It's the distance the car moves while the person reacts, or while between them seeing a hazard and putting their foot on the brake. So check yourself when you're asked thinking distance or braking distance. It's not a time, it's a distance. And it's a really common mistake. So you've got to start that sentence with, it's the distance. And then you can say, while the car moves, from seeing the hazard, the person running in front of the car, oh my God, to putting their foot on the brake. And that's the end of the thinking distance between seeing something and putting your foot on the brake. It's not the time taken. It's affected by your reaction time, but it's not your reaction time. It's just the distance the car's moved while you're thinking. Now, the braking distance is the distance the car moves from the moment your foot hits the brake until the car stops. 0 speed. You can just say the distance the car travels under braking, which means while your foot's on the brake. Right. Okay, you know what's coming. Guys, thinking distance. Can you tell me 3 things quickly, or 4 things that affect both? You could get a 6 marker on this. Easy peasy 6 marker. If you're doing foundation, likely to come up. This kind of thing. 3 or 4 things that affect the thinking distance. Drugs, alcohol. Tiredness. Make sure you use descriptive words. Genetics, reaction time. Oh, guys, make sure, actually, if you say just alcohol, they might not give you the mark. Maybe they say if someone has been drinking alcohol. They can be really strict. Even on the mark scheme, it just says alcohol, drugs. Say if someone has taken drugs, if someone has taken alcohol, if someone is tired, that kind of thing. Distracted is a good one. I would give an example. Playing on their mobile phone. So looking out the window at something. Listening to music. So I would give examples. The big one that's a misconception, another misconception, is speed of the car. Everyone is like, what are you on about? Right? When you write this, a lot of people are like, how can the speed of the car affect your thinking? It doesn't. Right? It doesn't. But if you're driving at say I'm driving at 50 miles an hour and someone runs out in front of my car, and my reactions, let's say they're a bit slow, they're a bit crap, they're 0.5 seconds, which is pretty slow. You guys are a lot younger, you'll have quicker reactions than me, so age is going to affect your thinking distance. Old people have to drive really slowly like this because your reactions decrease. So my reactions are a lot worse than yours. So let's say my reactions are 0.5 seconds and I'm traveling at 50 miles an hour. I put my foot on the brake. My car will have travelled further at 50 miles an hour in half a second than it would at 10 miles an hour. So if I'm driving at 10 miles an hour, my reactions are the same, 0.5 seconds, I'm not going to travel so far. So speed of the car, you travel further in the time that you're thinking. So speed of the car is one of the factors. Now, for braking distance, weather. Listen, Galland XYT, I would, with the weather, just be really careful. Give an example. If you just say weather, I would say like icy road, right? Slippery road, from rain. I would give an example. So every time you want to write something, give an example. If you say tires, they're going to say you're a joker. I'm not giving you the marks. You need to say worn out tires, okay? Worn tires, bald tires, and it depends if they're saying what will increase it or decrease it. If they say what will increase it or decrease the distance, then really good quality tires, quality of tires, quality of brakes. These are all things that will affect it. Okay. Road conditions. Please don't just write road conditions though. You can do it as a reminder, but check the question. The question might be like, what's going to increase or decrease the braking distance? If the road has got lots of grip, the grip on the road, say it. Or if the tyres have grip, say they've got good grips and things like that. Give a description. Cool. Speed, by the way, is for both. Speed of car is for both. Alright, let's move off of this. Oh, what other equations can they bring into this? Well, it's distance. I could bring into force equals mass times acceleration, and then we could do something where we end up with a distance. We could bring in, speed, time, distance, just a simple velocity, or the dreaded acceleration equations we were looking at. They could link to this. What the hell is this? I don't even... Oh, momentum. Right. I think I might just do momentum and then stop there, guys. Yeah, that's the dreaded equation. No. Strength of the brakes. Yeah, quality. I would say quality of the brakes or condition of the brakes. Now, momentum. Let's check out momentum. So, who knows the equation for momentum? You're going to get it. Another stupid physicist thing. They love it, don't they? They love mass times velocity. You know, like, let's use a P. Let's use a P. Yeah. What physicist came up with that? Right. Anyway, momentum is measured in kg ms. And remember, you don't need to worry about that. I keep forgetting you guys are being given all of this stuff. Mass is kilograms, so if you're given grams, make sure that you turn it into kilograms before you work out the momentum. Velocity is meters per second. You're 100% going to get a couple of conversions from units. You know, they're going to do that. Every single physics paper will have conversions. Okay. Momentum. Right. Let's just check a couple of things. So let's check your skills on the old momentumous. Who can calculate the momentum of this ball? Who's first to calculate the momentum of ball A? $99. Awesome. Thank you. 15, 15, 15. Superbulous, guys. Alright, nice one. Great. Who can calculate the momentum of ball B? Ball B's a little smaller, but no less impressive. He's going at 2 meters a second. So what is the momentum of ball B? Yep, awesome, awesome, awesome. Right, guys, I'm going to ask you a question. Someone who's first to tell me the total momentum. What is the total momentum? Someone is super smarty pants. Who came up with 9 first of E? Troll time. 9. Super smarty pants. Not 23, because look, I gave them direction. Momentum is a vector quantity. Why is momentum a vector? Can anyone tell me what element of momentum? It's got velocity in it. And when we put a V in something, you're damn right that's going to end up being a vector quantity, because we've got the V in there as part of it. So it's a vector quantity. It has direction as well, so we have to count one of them as minus. Doesn't really matter which one you put as minus or whatever. But the total momentum is 9. So superbulous. No, it's not 9, is it? 15 minus 8? Hello, hello. How do we get 9? It's 15 minus 8. I thought you were on the right track there. It's 7. Oh my good gosh. Right. Yeah. That's the combined mass. Awesome. total momentum of these bad boys, and we're going to do combined mass in a second. Okay, we're going to combine the mass in a second. Total momentum is 7. And now here comes the higher question here. You need to know this law. If you're getting momentum, you're getting momentum on Friday, guys. It's coming up, right? It comes up, and you'll need to know the law of momentum. Anyone know the law of momentum? Yeah, it shows me for not checking the answer. Right, momentum before, you might say, before what? But before an event, basically, equals momentum after. So, what events, what's happening? What's happening? Well, they're going to have a little crash. So these bad boys are going to crash into each other. Who's going to be the first person to tell me what the new velocity and direction is? They're not going to go... Now they're either going that way or they're going that way. Who's going to work it out? The momentum before equals momentum after. Now we've got to skip back to the first momentum equation, combine everything and work it out. So we know this is 5 kg. We know this is 4 kg. So we have a new total mass of 9 kg. We know that before the momentum was 7. So after, total momentum is also 7 kg meters per second. So now we're going to rearrange, whack it into the P equals M times V over here. And if I want to find, I have P is total momentum. I have mass is 9, so I'm going to do 7 divided by 9, and that's going to give me the velocity. Not divided by 5 are AG, very near, yeah, we got to combine the masses. So, oh yeah, you're probably on that, right. So yeah, what is that? So it's 0.77. And we've got the direction. We've got the direction, or 0.78 meters per second. It's a positive number. So as it's a positive, yeah, 0.7 recurring bro moment. So as it's a positive number, it's going to the right still. It's in our forwards direction, which we assigned a positive at the start because we minus 8 from 15. So yeah, whatever. It's going that way. Cool, great. You guys are on it. Now, the next thing, I'm going to wipe this from the screen. Here's the next one. Very common question. This kind of question, it not necessarily in this scenario. You can use 100 scenarios. Okay, so gun is stationary before. I don't really need to tell you that. So they might leave that for you to work out yourself, but they do like to be kind. So in the question, I really recommend highlighters, because you're not going to lose anything from highlighting things, and a keyword like stationary is vital in forces. So if you've got AQA and you're doing forces, the word stationary is coming up in one of your questions, and it's going to give you the answer, help you reach the answer. Gun is stationary before being fired. The bullet leaves the gun forwards. Explain using ideas about, oh my good gosh, momentum, why the gun moves back. Hasn't been a gun invented that doesn't have recoil and move back. And this is at least 3 marks, possibly 4, but will be part of a bigger question. So your bullet leaves the gun. Explain using your ideas about momentum. Why does my gun have to move backwards? Yeah. The momentum backward cancels out the forward momentum, but you're going to need a little bit more than that. You could argue this with Newton's laws. You could argue it. But specifically here, I've said use ideas about momentum. And you'd have to actually say the bits. No, what we do here, we're using ideas on momentum here, but sometimes, AG, they may ask you to combine Newton's laws. Here's the actual momentum answer if you want to explain it using momentum. So, someone said, momentum before, this will get you 1 mark for just quoting the law of momentum. Momentum before is equal to momentum after. Right? So, 1 mark. What was the momentum before? Read the question carefully. What was the momentum? Ooh, M is on fire. Momentum is 0 because it was stationary. So momentum before is 0 as it was stationary. So that means if the momentum before was 0, our momentum after must be 0. Total momentum. We're not talking individual momentums. The momentum of the gun and the bullet when they were friends and together was 0. When the bullet left the gun, it had a forward momentum. The gun must have a backward momentum because when we add them back together, they must still equal 0. So the total momentum after equals 0. So the gun has to have a backwards or negative, you can use the word negative, have a backwards momentum to cancel out the forwards momentum of bullet. I've definitely gone above and beyond. Now with that one I've gone a bit extra, but yeah, so if you imagine this has gone forward at 5 kilograms, I mean the bullet is not going to travel at that, no, it could well more than that, a lot more than that, 5 kilograms per meter second. My gun has to, because it was stationary beforehand, move back at 5 kilograms per meter second. Obviously the velocity element, the meters a second element, the gun is like 100 times heavier than the bullet, so the gun is going to move back 100 times slower, but it's still going to go backwards. The direction has to be backwards because the total momentums must cancel out. So if this is backwards or negative, then this is forwards. So plus 5 minus 5 equals 0. So watch out for that. That comes in a lot of incarnations. Here's an example, guys. So swimmer, this young lady is jumping off a boat. What 2 factors define the momentum of the swimmer? What 2 things? What's the momentum of the swimmer? What 2 quantities? I've got a leak in the roof. It's to hide my bald head. No, I am actually bald, but no, I like wearing caps sometimes. I love hats. I'm a cap person because I've got a bald head. With a bald head in this heat, my head goes red like this pen, and I shed my skin like a snake. So I got used to wearing hats to protect me, even on like a normal day. You've got light skin, very light skin. I don't have any melanin. I do have melanin. I'm not albino or anything, but I don't have a lot of melatonin or whatever the protein is that protects you from the sunlight, being of a very light. And I went bald at like 21. So I started losing my hair at like 21. So I shaved my head way back then. But basically, if you just keep, that means when I walk to the shops, even in the winter, my head is exposed to ultraviolet radiation on a regular basis. And I'm supposed to wear sunglasses all the time as well, actually, because I've got a little thing in one of my eyes that could become a cancer if I don't wear sunglasses, but I never do. Right, it's mass and velocity that determine the momentum of the swimmer. What's the unit of momentum? Which one, guys? It is more convenient. I haven't had bald is awesome. Bald's awesome. Honestly, it was one of the best things that happened to me was going bald. But I nearly cried about it when I was like 21 at the time, and I loved my hair. I used to spend hours doing my hair in the mornings. And like I was going on an escalator in London, on one of the escalators, and one of my friends was standing like 10 meters above me, and he looked down and went, "You're going bald." I said, "You're on drugs. I'm 21. I'm not going bald." And then I looked in one of those mirrors they have in the tube station up in the corner so they can see what's going on, and I was going bald. And I went to my doctor and I nearly burst into tears. I said to her, like, what's going on? What's going on? And she said, tough. You got genetic balding. There's nothing you can do about it. So, but you know, after about 6 months, I got over it, shaved my head and was like, yeah, awesome. Love it. Best thing ever. But it wasn't at the time. I was devastated. Right. This is the exact, I'm not going over this one, guys. This is the exact same thing. I just wanted to show you. The boat is stationary. So pick up on the word stationary because it means we're talking about momentum, that the total momentum is zero before. And if the total momentum's, and then it says she dives off. Look, I'm going to get off my chair. Watch. The chair moves backwards. You get off your chair has to move backwards because if you're sitting still, you've got zero momentum because zero velocity times mass equals zero momentum. So if you're sitting still, you have zero momentum. When you step forward off your chair must move back a bit because you've got forward momentum. The backwards momentum of the chair cancels out your forwards momentum to still equal zero. So we want to say the exact same answer as before. As the swimmer dives forwards, the boat moves backwards. So it's the same as the gun one. Total momentum before is zero. She has forwards momentum. I'm wording this slightly different, but in order for total momentum after to equal zero, boat must have negative momentum. Okay, negative or backwards momentum. Because we still have to conserve the momentum. The law of momentum says it has to be conserved. So in order to conserve it, if she has a forward momentum, the boat must go backwards. And then it conserves the momentum. 4 marks. Boom. Yeah. Right, guys. I think I am going to finish there. Oh, one other thing. Very last thing before I finish. I'm about to finish. I don't really do Newton's laws, but never mind. Okay, car crash, alright, you have to know, now these can come in lots of forms, so airbags, seat belts, crumple zones. Oh, Karam, you can use Newton's laws, but look at the wording of the question. It may say use ideas about momentum. Recently, they've actually started combining the two and said use ideas of Newton's laws and momentum. So you can use both. You can combine them both. And they'll often do this for like two balls which hit each other. And then they'll say like ball A is moving at 50 miles an hour and ball B is moving at 20 miles an hour. Ball A collides into ball B, use idea 6 marks, use Newton's laws and ideas to explain what happens. And obviously we get an equal and opposite force and stuff like that. So one ball slows down, one ball speeds up, gains the momentum from that, and because the total momentum has to be the same after. If they're going in the same direction, you see you get a different result. One doesn't necessarily move backwards. If they're both going in the same direction and you have a collision, this one is just going to slow down, and you know, and you can use Newton's forces to explain the equal and opposite forces for that, and then you can use momentum as well, so you can kind of mix and blend. With this one, this is change in momentum. This is purely to explain accidents. Sometimes they want you to do this over time equals force. Now, you need to be aware if you're doing AQA that forces cause injuries. The force on a passenger causes an injury. I used to think, oh, a seatbelt absorbs the energy. Because it's elastic and it moves, it absorbs the kinetic energy from your body and transfers it into elastic energy. It actually does, but they often don't want that. They want you to describe how a seatbelt, an airbag, a helmet, a knee pad, an elbow pad work when you have a fall and how they reduce the force. So really we want to talk about how is force reduced. Well, let's just say that the change in momentum is 10 and the time taken is 2. What is my force? 10 divided by 2, my force is 5 newtons. Okay, that's the same as being hit in the head by 5 apples. That's not going to damage you. So we should think of it as like 10,000 divided by 2, but never mind. This is just to get the point across. What happens if I have the same change in momentum, but I double the time from 2 seconds to 4 seconds? What happens to the force? Smaller force, thanks. And the smaller force means you have less chance of an injury. So if you're asked why your baby sister or brother rides their bike and they've got a helmet on their head, and when they fall, how does the helmet protect them? People want to start going, oh, well, you know, the elastic energy, oh, it stops their head hitting the floor. No, it doesn't. Doesn't stop. Their head hits the floor, right? Your seatbelt ain't going to stop your head bouncing off the front of the car, okay? When you have an accident at speed, your head's going to hit the dashboard in the car. The driver's going to hit the steering wheel. What the airbag does is slow them down and increase the time for the change in momentum, reducing the force. And you need to explain that. So for the same change in momentum, the car's going to go to 0 anyway. So the change, if the car has 500 kilograms meter second as its momentum, when you have a crash, it's going to 0. So the change in momentum is 500. If you can increase the time that that takes, you'll get a smaller force. So if all an airbag does, rather than talking about changes in energy, you need to say it increases the time taken for the change in momentum, which reduces the force. A smaller force means less injury, and that's what happens. Yeah, I'm going to bed. So, yeah. Someone punches you in the face with a boxing glove. How does a boxing glove work? Same thing. The fist inside the boxing glove is still going to hit your face. The actual bones are still going to come through and they're going to hit your face. But the boxing glove is going to increase the time taken for the change in momentum and decrease the force. The helmet that a boxer wears is going to decrease the time taken for the change in momentum and decrease the force, less injury. So that's how all of those situations work. If you're wearing knee pads and you fall on your knees, it's how the knee pads work. It's how cushioning works. So you have to use this. Yes. You can say decreases the rate of change of momentum, which decreases the overall force, and then finish it with less force means less likely to be injured. Yeah, I'm going to bed. Right, guys, tomorrow I'm doing electromagnetic waves. Now, waves come up in AQA. And waves are coming up in another exam board. I can't remember if it's EdXL or OCR. And then I'm definitely going to do magnetism and electromagnetism tomorrow. And I'm going to have timestamps on this if you want to flick through and watch any of this. If you didn't catch the start of this on forces. And I might do some other forces. But yeah, I'm definitely going to do magnetism, electromagnetism and waves tomorrow. And maybe some other stuff. But yeah. I don't know whether to start at 8 or whether to start at 7. What's better? Bro moment, maybe it won't be on the exam, in which case great, forces aren't there, but some of it has to be on the exam. Although, so some things I've gone up with, again, it's like that, you know, some people are like, sir, you went over chromatography. If you were there for the chromatography, they were like a 6 marker came up on it. So when I did the C2, and when I did the P1, I don't know, some crap came up. People were like, oh, sir, this came up. But really, I'm covering everything. So everyone's always going to say, oh, sir, thanks. You went over that and that came up. The only problem is they could ask it in a different way. So, yeah. Anyway, nice one. What do I predict? Pain. No, tears and pain. It's most people's last exam, so it's a good thing. I would just say... yeah, I haven't done a prediction on this. I might look tomorrow and then say what I think's coming up. By then it's too late though. Take me about an hour. Like I said, you've got to go through each exam paper and see what hasn't come up. You've got to use your revision guide. If you weren't here at the start, Got to use your revision guide, either combined or separate, and open up all the 5 exam papers that are on the AQA website, look at them, and put a light, like look at what's come up and what hasn't come up. You could then predict this isn't going to come, like this is going to, but then I do that for C1 and then found that in the last 5 years electrolysis came up every single year, so they every single year guaranteed ask an electrolysis question. And then for other things it's like they come in little twos, like they'll do momentum for 2 years in a row, then won't do it for 2 years, then they'll do momentum again for 2 years in a row. So it's kind of weird, but you can at least see what hasn't come up and then see like, oh, they haven't asked that in ages, that might come up. A lot of that worked, but it's just predictions. I would just say revise everything. All right, guys. Yeah, troll time. Be careful with that. Yeah, she might not thank you. All right, night. Good luck, guys. Keep working hard and really relax and enjoy the summer. Over the summer, I am going to do weekly lives for biology A level and chemistry. For those of you that are sick enough in the head to want to take biology, chemistry, and A level, I'm going to start weekly lives as like an introduction to the course. Because and then in September, I'm going to be doing weekly lives just to supplement what people are doing in AS and A2, so for year 13s and year 12s. For chemistry and biology. They're not going to be in the same format as this. They're going to be, obviously, this is trying to cover as much of a course in a couple of hours. It's crazy, really, because you spend, forces would be taught over like, in school, you do forces for like 6 weeks, 10 weeks. And remember, in school, you get 5 hours a week of science. So you're talking 50 hours to teach forces, or 40 hours to teach forces, obviously with all the practicals and that, and you break it down and do more detail. So when I do the A level, it's going to be lesson by lesson, like just one lesson on cells, one live on this, one live on that. But for those of you that want to be yeah, look out in the summer. But I would recommend just relaxing in the summer and picking up your A levels, but some people want to start early. So cool. All right, take care, guys. Good luck. Oh my god, there's 2 of me. Incredible.